Good morning, everyone. I hope you are all doing good. Let's start the presentation with an apology that unfortunately, due to unexpected reasons, I am unable to join you in person today. However, I'm happy to present my work virtually and I look forward to your questions and feedback. My name is Hamad Rafiq and my co-authors are David Patti, Maurizio Palesi, Gaetano Carmelo Ladelfa. Thank you for being here. In this presentation, I will be discussing smartphone-based indoor localization system, which is a key technology for improving navigation where GPS is weak or unavailable. I will introduce our proposed solution, which enhances accuracy by fusing visuals with magnetic signals to improve indoor localization while using the vision transformer. Before I begin, I would like to thank RECIT, Future Artificial Intelligence Research, for their funding and my university, University of Catania, for their continuous resource support toward their resources. So let's begin the introduction. So before studying or before exploring the indoor localization, there was a question, what are the factors basically that can improve indoor positioning? These questions help us to explore different techniques or technologies to check how it works in an indoor localization system. And it helps us in exploring indoor navigation using magnetic field signals with visual images. The concept of integrating images with magnetic field signal is basically inspired by human perception, where localizations are often identified quickly by examining the visual images. Through experiments, we realized that projecting magnetic field signals on visual images can enhance the localization. As we can see into this figure, we can see that the blue line basically represents the raw images, while the orange line is representing the fused measurement, which is the images fused or projected with the magnetic field signal. So, when we project the magnetic field signals on images, it enhances the features and improves our understanding of the environment. For example, the alignment of the fused data clearly highlights a long corridor from point 5 to point 34, and also it highlights a small corridors of the steady environment. Hence, when we talk about that magnetic field signals provide us spatial information, it can be confirmed from this thing that the spatial information provided by the magnetic field signals is improving the model interpretability and reflecting directional changes in the mobile phone. Hence, based on these outcomes, we come up with an idea to introduce uh, a model called multi-head attention vision transformer for smartphone-based indoor localization. Even we can see the heat map of the long corridor here with a small corridor on the sides. Now we will talk about the proposed system architecture or the proposed model. In the beginning, first we will discuss about the general flowchart, how it works. It takes the input images and magnetic field signals, go for the pre-processing in the offline mode, and then produce the fused measurements or the fused fingerprints, which will be used for the model training. And in the similar fashion, in an online phase, we use the same images and magnetic field signals, which will be going through the same pre-processing for the prediction using the trained model. So before talking about the components of the magnetic field signals, I will just say that we just follow the conventional methods of collecting the data from the steady environment. From different reference points, we collect the magnetic field signals and the images in a vertical angle of the mobile phone. So if we see the components of the magnetic field signal in figure 3, we can see that we have four major components. One is the 3A, 3B, 3C, and 3D. In the figure 3A, we are basically providing the visual feature extractor. In 3B, it is helping us in getting up input data for the projection model in a specifically arranged data set, specifically arranged form. And magnetic field 1 is aligned with the image 1, magnetic field 2 is aligned with the image 2, and so on. And in the 3C, we are having the proposed magnetic feature projection model, who is projecting the magnetic field signals on the images to give us the projected data, which will be used as an input for the encoder to further generate the output. Here, we will talk about two of the major components of the proposed system architecture. First, we can see that after collecting the images and magnetic field signal, we start by extracting the images feature. For this, we basically use the pre-trained vision transformer based model, which is generating features for us of 768 dimension. After that, each feature vector is basically concatenated with magnetic field signals in a way that each magnetic signal MI is paired with the MI or the features of the image. Specifically saying, the ith magnetic field signal is associated with the I modulus mth image, which forms the ID dataset as shown in this equation 3. So why we did this thing? This pairing basically enables the model's encoder to better capture spatial relationship and dependencies as well. Moreover, this approach was adopted to address the sequential related problems, which basically encoder block faces. It ensures that each image is paired with its corresponding magnetic field signal, and it enhances the understanding of the environment, leading to, for example, the better accuracy. Then the next step is basically the proposed magnetic feature projection model, which is taking this ID, specifically in dataset, and what it is doing is that it is basically projecting the magnetic field signals onto the feature vector of the images, which results in the projected or the final fingerprints, which we termed as a fused measurement in the article. The length of this PD is basically the image feature length minus the magnetic features, because we did the element-wise addition of the magnetic features on the image features. This approach utilized magnetic field signals as position-dependent signals, which helps in compensation for the lack of positional information in the encoder block. Furthermore, we will talk about the training model after doing the pre-processing and extracting the feature and doing the projection of the images with the magnetic field signal. Here we will see our training loss of our proposed model, which shows that the model converged to 30, and these are the 30th epochs, and these are the parameters which we use for the model training for our MH field model. So let's talk about some results. We evaluated the proposed model on three different datasets. For example, you can see here, this is the fused measurement, which has projected magnetic field signals on the images, only images, and only magnetic field signal. So we can see the error rate as well, and the error rate as well in the bar charts and the box plot. So this is basically showing the confusion matrix, which shows that our proposed model basically in the beginning it basically shows some results which are not good. However, this is because here we have a door which is very plain, and our model was unable to extract a specific, or you can say, or struggled in extracting the substantial information which can be useful for predicting the location. So now we will talk about some more results which we achieved, which in terms of computational complexities of the proposed model. Figure 7 is basically presenting the G-flops of our proposed model. So these blue circles are basically presenting the parameters. Bigger the circle, more the parameters, which means the model is not good because it has a lot of parameters to do. Smaller the circles, the better the model. So, and smaller the error, the better the model. So this red one are showing the model which are using vision transformer, and this gray one is the model which uses multi-head encoder in their models. So in both senses, our model has a very less parameter, and it is outperforming the model which is using vision transformer. And this is the output in a steady environment which we use for the evaluation of our model. And this red circle you can see here, which was not exactly classified by the model, because this is the door which was not helping the models in extracting some specific information so that it can do the prediction based on these images or the data. Now, in the end, we will talk about some more results, which are basically the cumulative distributed function, which shows that the blue one is the model which is trained on the fuse measurement in comparison with the model which is trained on only images and the only magnetic field signals. The model, you can see the trained on magnetic field signals perform the worst. It is due to the limited data set and complexity of the magnetic field signals of the limited components. Since the proposed model is built upon the Vision transformer, so it benefits significantly from the large dataset, which highlights the shortcoming of the magnetic field signal alone. So we can say that because of the Vision transformer approach, we don't have the very big dataset for the magnetic field signals, and hence it is not performing as per the expectations which we were doing in the images or in the fuse measurement. So if we see the tabular results, it shows that we have the confidence interval of 95% that the proposed error will be between 0.08 and zero point 0.5 meter for the one which is achieved on the fuse measurement. Whereas for the magnetic field signals and visual images, it has a bit higher error rate confidence interval. So 92% was the accuracy achieved by the fuse measurement by our proposed model with the error rate of 0.29 as compared to the magnetic field signal alone and the visual images. So in the end, we will talk about some conclusions and the future work. We basically try to introduce a magnetic multi-head vision transformer model in order to improve the indoor localization. We use vision transformer with the encoder for the position classification, and then we proposed a magnetic feature projection model. That is basically the main part, and fuse the magnetic field signals on the visual images. In the future, we are interested in exploring the limits of the model to find the best parameter for handling the complex data set. And similarly, furthermore, we are more interested in working in an environment where we can feed the blurry images to the model or the images in a different angles or the one with the light effect. And similarly, we are more interested in checking how the light on the images might influence the indoor environment. Either it improves the accuracy or it reduces the accuracy. So this is all from my side. If you have any question, then you are more than welcome, and I'm here to answer everyone. Thank you very much from my side.